Okay, welcome to this extra section in time series analysis. I'm going to give today mostly just some examples, and I will do one video per example. So the first example regards an interesting project on mink and muskrats, and the data dates back to the early 1900s of fur farming in Canada. It's basically first sales over a 61-year period, and you can get all the data and everything there if you like. So this is basically what we have. What happens is, well, mink likes to eat muskrats, and if they're so muskrats will reduce the number of mink will reduce the number of muskrats. On the other hand, if the muskrat population increases, there'll be more mink. So that is basically the model that we're looking at. Now let's swap to R. That's where we want to be most of the time. So I've prepared a small script just to carry us through. So the years we have here. What will read the data is mink from a file. We'll skip the first 3 lines with just a header. Same thing for the muskrat. Since this comes into the table, we will also just take the first column. Could have used scan instead, but I just prefer to use read table. Now this is a time series, so we'll make it a time series starting in 1850 with one observation per year. So that's why I said frequency equals to 1. Same thing for muskrat. And then I'll combine it into just one piece of data. And I always like to have a summary. So we have some numbers here, and we see that mink are vastly outnumbered by muskrat skins that are traded, but yeah, that's just how life is. Now plotting a time series object, what we get is data like this, and we get one for the mink and one for the muskrat. Maybe if we zoom in, it's easier to see. So we definitely see some patterns here. Now these are not seasonal, but they are nevertheless there. And we also see some patterns here for the muskrat. What we also see is that the variation here in the beginning for the muskrat is small, but towards the end it seems to be larger. Whereas for the mink, the variation, well, it may be, but the process as such is more stationary. So I think what would make sense is to make a transformation, and well, the usual transformation to make in a case like this is a log transform. So that's the next thing we'll do. Make a log transform, call that L data, just to get a summary. Now by default they'll keep their names, but to avoid confusion later on, I want to call them L mink and L muskrat, L for logarithm. See what happens. Yes, that's what we anticipated. Let's plot the data again. Now things look a little bit more, well, the mink are still looking nice, and the muskrat, the variation has been at least it's less now than what it used to be. Now, how are we going to model this? Well, we have 2 series, so why don't we consider something multivariate? First thing, we need to consider what is the order. So let's plot the autocorrelation functions. Let's zoom in again. And what we see here is for the log mink, we do see some damped oscillation. Likewise for the muskrat, we see some oscillations, and we also see them in the cross correlation going forward and backward in time. So this corresponds very well, and the season of this peak is about 10 years. Maybe you could say the peak is probably a little bit before 10 years. So that's what we are looking at. Let's just add the partial autocorrelation function as well, which we have here. And what we look at here for the mink, we see there's something in lag 1 and something in lag 3. This out here is probably just noise. For the muskrat, there's a lot in lag 1, something in lag 2, and that's probably most of it. For the cross covariance, if you look forward in time, there's virtually nothing. Backward in time, here we have a lag -1, we have something, and lag -2, we have something. So now, what is a good model? Well, the highest number where we see something is of order 3. So that might be a good guess. But we also see there's a lot of things that are not there when we go to lag 3. So what is the best model is, at least for now, an open question. Sorry, there was one thing I didn't mention before, which will kind of go back one here to the data. One can discuss whether the mink seems to be stationary, whereas the muskrat seems to have an increasing trend. Potentially. Now, we don't know right now if we're going to need that or not, but if you follow the example from the book, that they will make it one-step differencing of the muskrat. So differencing of the logarithm, well, what does that become? Well, that's the log of the relative change from one year to the other year, the following year. So we will make a new one where we have log of mink and diff of log of muskrat. Now when we do it with a c-bind here, this diff will return a series that is one step shorter, but when we c-bind it, due to that these muskrat and mink are time series, they will be nicely aligned. Again, I'll just pick the right, maybe if we just see the head of difference L data. So what we see that automatically puts in an NA here, and let's get a summary as well. So now these things have just changed. The function that we're going to use, to fit, will not allow NA, so we will do an NA.omit to remove any line that has an NA in it. First thing, let's just look at the autocorrelation again for this series. We have it here. It looks sort of similar. There's a little bit less down here at the muskrat, not unexpectedly, since yeah, we did a differencing. So, and since now we just have something in lag -1 there, and what we have there. So let's look at the partial. Maybe we can just see it here. Well, there's definitely something in lag 1 there, still something in lag 3, lag -1, potentially lag -2, nothing, maybe a little bit there, but not a whole lot. Now, we've mostly used ARMA so far, but the AR function, if we only go for an AR part, which since we started off seeing something that was damped exponential, we should consider AR parts. Let's do this. Now, max order 10 sounds maybe a little bit high. The default is actually higher, but what AR does is to automatically pick the one with the lowest AIC. So let's just look at it for a moment. What we have here is an AR, and it becomes an AR1 to 3 multivariate. So this is the matrix for the AR1 part, and for the lag 1, for lag 2, and for lag 3, how dependent it is. And like in the end here, we have the noise, the estimated of the covariance matrix for the noise that goes into the AR part. So this is basically just an AR, a multivariate or bivariate AR3 process that should be the best fit according to AIC. Now, usually I like to see some standard deviations and other pieces of information of parameters, and you usually get that by doing a summary of a model. Unfortunately, that is not here. So basically what we get instead is a list of all the things that are in there. Now, one thing that could be interesting is AIC, which is basically what is used to predict. So let's go in and look at the AIC values. So this is what we have in here relative to the best model, which was model 3. So, or an vector AR tree. So an AR2 model is slightly worse, and AR4 model is even more worse. So this is what we're looking at from this perspective. Now, is this a good model? What we have to do is basically to go back to the slide and say, well, validation. Same thing as what we've done before. We look at the autocorrelation function, we look at the partial autocorrelation function, sign test, distribution of residuals, and whatnot. And we should also look at the cross correlation. But everything else is pretty much like what we did for the univariate models. So let's look at the residuals. We omit the NAs. So what we're looking at here, well, of course there should be something like 0, but that's about it. Going to the muskrat, looks nice. Everything looks quite nice. If you look at the partial autocorrelation function, well, I mean, there's one sticking out there, and maybe one, well, like -14, I really don't care much, in this case at least, and this is also very fine. Well, it is just one test for normality. We'll do the Kolmogorov-Smirnov test, taking the residual one column at a time, and dividing by the standard deviation of the same, and compare with the probability of a normal distribution. This was for the first column, which was a mink. We have a p-value that is larger than 0.05, so we cannot reject on a 5% level that they are normally distributed. And if we go for the second variable, well, we get an even higher p-value, so we cannot reject independence or normality. I forgot to mention that what we look at over here is the cross correlation between the residuals, and these are the autocorrelations that you could say are used to look at. So this was basically one way of approaching this. What is not included in this part is looking at what happens with the parameters. Are they all significant or not? You can say from the initial look at the partial autocorrelation function, there are probably some that are not significant, but not much we can do about it right now. But in R, there are more packages. So AR is basically just one package for this. Another package is the one called VARS for, well, vector autoregressive models. Load that library, and just to fit a similar model, we take the same data set as before, and I want to have an ordered tree model. Maybe we should just briefly look at the help page for this, because it's somewhat different from what is in the AR model. Maybe I should just go back to the summary of the auto model. We could just take var.auto $x_mean. So what it does here is that it calculates the mean value of the two different processes, and that's about it. Which for the var model, var function here, notice that it's uppercase WAR. It takes a multivariate time series. It takes the order that's going to fit, and then you can include, do you want a constant, as in the x_mean over here? Do you want a trend, as in a slope over time? Do you want both or none? There's also a way to do seasonal models, and you can also add extra predictors if you have that. And like max is not used here. And then we have some information criteria. We just before used AIC. The SC is what is usually, in my book, called the Bayesian information criteria, BIC. There's a final prediction method here, and this is, you can say generally AIC prefers larger models than the BIC, but that's how things are. So this is what we're looking at, to try. So let's just go ahead and run this. So the default we get here is structures a little bit different. So here there's first for mink, there is this expression and the associated parameters that goes with that. So the dependence on the lag 1 mink is 0.72. The lag 1 difference logged muskrat is 0.43. Similar for lag 2 and for lag 3, and then the estimated mean or constant for this process. So it's a different constant. It's a different process as such. So the parameters are also somewhat different, but not too different. Let's just look at the first set here. So for mink, mink, depending on itself, is 0.72 and 43 on the other. Let's see if we can just scroll up and find it. Whoops, that's where we got it. So the mink on mink, well, 0.74 and 0.41 similar. And for the DL muskrat, well, it's minus 0.72 and 0.23. For the muskrat, it's minus, well, obviously quite close within a little bit of uncertainty. Just formulated in a you could say, so these are presenting it univariately. And here we can get a summary. So what we get here is, well, first of all, a lot. We start off with, this is what we've done. Then we have the sample size, nice to know, log likelihood, and we have the root of the characteristic polynomial, and we have how it is called. We have the same, you can say, equation for log mink, but now we get the estimates, their associated standard errors, and we get, well, t-values that are then related into p-values. So what we see is that the constant is very significant, so is the lag 1 here, and lag 3 for mink, which was also what we saw if we go back for the plots. This was the partial autocoil. No, this was for the errors. Let's go back. Here we have the series. So this is probably coming from this lag 3 here. So not surprisingly, and if we go back or go to the other, the differenced log muskrat series here, basically all we see is the constant is significant and the lag 1 is significant, and then there's everything else is not significant. But by AIC in the first model, that was the best model. Now, we of course also get some estimate of the covariance matrix between the different series. Again, this is similar, but not exact same values. Mostly because the constant is implemented in a different way. Okay. Now, this was a manual, and we could go through and do this for every model that we could imagine, every order, but there is a var select function that kind of does the same thing. Now I just told it to drop to maximum lag 6, because we learned before that was where we wanted to be going, and not to spam the screen too much. Now we get the AIC and the other, first you can say information criteria and the final prediction error for models of lag 1, or of order 1, 2, 3, 4, 5, 6. And the model we just looked at was this model here. Now we want to find the best model AIC wise. We're going to want to find the smallest numbers. That will be number 6 out here, which is why there's a 6 up here. So by AIC, an order 6 model is the best, but by BIC, a model of order 1 is the best. And from looking at the parameters we estimated just before, let's just see how this performs. This was for the model with differencing of the muskrat. We were kind of discussing, is that needed? So I'll make the same selection here for the one where we just took a logarithm of both series. We get similar results in a sense. With AIC picks a larger model than BIC, which is what we should expect. So let's just see how order 1 models behave for both kinds of input series. So we have a model here. We should probably just do summaries of both models one at a time. So the one with the difference, we start up here and we see that all parameters are significant in this model, and whereas for the DL muskrat, the muskrat difference doesn't depend on the previous muskrat, but only on the previous mink. Again, there's a constant. And residuals. If we go for the non-difference model and do the same thing, well, basically we get something that is slightly different here. The constant is not significant, but we'll just leave it in for now. But at least for the mink, but for the log muskrat, everything has become significant. And there is a very significant dependence on the previous log muskrat. Well, you can say, since before we made a differencing, it should not be a surprise that there is currently some dependence on the lag 1. But you can say what is differencing corresponds to an estimate of 1. The value that we get here is 0.87 with a standard error of 0.07. Well, 2 standard errors brings us just on the other side of 1. So you can say we cannot reject that it could be 1, but we cannot say that it is 1 either. So how to select which model is better? That's the question. Now, you're not going to answer right now, so what I will do is just show you one part of the documentation of the vars package for the var function. The outcome of that, return of that function, is an object of class vars. I'll show you how to get that. And then there's a lot of different methods. So that's why what I did so far was to make a summary of my model. We could also get the residuals, we could plot it, we could get the log likelihood, and other things. Printing it we've done. Now, what is that we want to do? Well, we want to investigate how the residuals are behaving. But we also got some functions out here. Some different tests that we can just perform. Test an arch is conditional heteroscedasticity, so that's saying is the variance homogeneous over time or does it vary over time. We can also test for normality, and we can test for correlation or serial dependence. So let's just go ahead and do that right now, one at a time. First, a serial test for the one with the differencing. What we see here is a pop and show test, which the same thing was done similar to the Young box test that kind of comes from the TS diag plots. We see a p-value here that is very small, so in this case we'll actually reject independence. If we do it for the non-differenced muskrat data, well, then we get a higher p-value and it's larger than 0.05, so we cannot reject our null hypothesis. We cannot say that there is correlation. And for the heteroscedasticity, we get a p-value that's actually very, very large, so there's no sign of that. nor for the other one. For normality, whoa, here we got, well, kurtosis is the fourth order moment, insignificant, skewness, insignificant, third order moment, and we also have another, the Jacques-Pirat test, not significant, and doing the same thing for the non-difference, just logarithm data. They are all non-significant, but now we actually ran 5 different tests, one at a time, which I think is a little bit too much work. So what I want to do is make my own test. First, it does the normality test, then it does the arch test, and just from and then I just want to get the p-value out, and the serial test, and then I return what I get. So when I run all my tests, then I get my Jacques-Pirat test value, the skewness, the kurtosis. Those were from the normality test, and then we get the arch chi-square test and the serial correlation chi-square test. Then we get it for the non-difference data. Maybe I should just do one thing different now. Now, as I mentioned, we also have a plotting function just to see what we have here. Right now, well, at least my recommendation is saying this model doesn't invalidate any of the assumptions. So the one that does not include differencing is better than the one that includes differencing. Let's make a plot. And now what happens to me is that I get an error right now. Figure margin is too large. And that's basically because it wants to add more graphics down here. So what I have to do is to just increase the size over here, and that was not enough. This only happens in RStudio, I've been told. Now I need to get rid of this. See if that was sufficient. Yes, but not so nice, I would say. Now it does one for, at first it does it for mink, and then when I hit enter it does the same thing for the muskrat, but we cannot see much down there. Let me just try if I can fix that. Par of, didn't I write that further up? Let me just find it. See if things looks better. It became better up there. Let's go over and look at it over here. At least here for the muskrat part here, we can see it down here that the partial autocorrelation function, there's nothing in the residuals. In the autocorrelation function, well, there's only like 0, so which should be there. And then we can see up here in black we have the data, and the blue line here is our fit. As often seen, the fit comes just after the data when something happens, but generally it looks quite nice. And let's just go back and change to the previous plot so that we can see it for the mink as well. See, now it's log mink, and here we see for the autocorrelation there's a little bit out of lag 10, which is the season that we observed initially. Likewise in the partial autocorrelation function, there's a little bit, you can say, dependence out there, but you can say everything else looks nice. You can say the systematic thing is probably this that reoccurs a little bit later every time, that there is kind of a gap where the black is slightly above the dashed line here, and then something different happens towards the end for some reason. And you can say, for some reason, well, that's just how life is. Let's round off with a summary of the data. Again, we did look at this. You can say the constant here is not significant, but that everything else actually looks very, very nice. And that was basically, I think, what we wanted to be doing. You can go back in here. Well, did we actually validate the model? We did do a little testing of the marginal distribution of the residuals. We didn't do a sign test, but we did other things. We looked at the autocorrelation function, and we looked at the partial autocorrelation function and the cross correlation function. So we did what we, you can say, told ourselves to do. What one could then spend more time on is, well, is the order tree model better in some sense, or how are these models relative to one another? We could do log likelihood testing since those two models are nested. We could also do one more thing, which I think we should just do, just for the comparison. Let's go up here. Now we focus on the non-difference data. I'll just copy this line to the end, because what we did was to look at having a constant here, but we could also consider having something different. I will just run it without saving stuff. So we had 4 different options here. The first one was constant. The second one was a trend, as you can see just underneath my picture. Third one is both, and the last one is none. What we want to look at now, since these different changes here is just adding either a mean value or a trend over the period, or both, or nothing, assuming both are 0, these things are actually nested. So we can actually compare these models. So what we want to look at is, let's just look at the BIC lag 1 model here, 5.01 for the constant function. It became less negative since we want the smallest model. The constant one is better. Having both became minus 0.11. Now what was it for the cost? Minus 5.01. So actually, which one is better? This, having both, is actually slightly better. Having none is worse, probably not unexpectedly. So let's just go up and look at both again. Again, the best model should be, for the BIC, the best model should be lag 1. So let's just do a model like that. Let's call it var dot var1 both. It should not be var select, just the var. We use the L data, and we use P is the second parameter just to make things nicer. We use an order 1 model. Let's see what we've got. Actually, let's get a summary of it. Just like that, we can see more of it. So what do we have here? Well, we see that the trend is significant for the mink, and we see the constant is significant for the muskrat. And since one is significant, very significant indeed here, so the fact that one is significant for one and the other for the other one, that's probably why you can say prefer to have both in there. Now one could of course consider to have models with one and the other, but for now I think we'll just close this session right now. So thank you for listening, and see you around. And now I should be able to